All right. Good afternoon, everyone. I'm super excited to be here with you today. And I hope that you're as excited as I am. So my name is Clement, or Clément, with the French accent. And today we are going to talk, and actually we are also going to write some Huff. So first I would like to ask you who knows what Huff is? Okay, so that's pretty nice. And whoever tried writing some Huff already? Okay, so we have a lot of beginners. That's perfect. One last question: are you knowledgeable? Do you know how blockchain works? Are you a developer? What would be do we have many beginners in blockchain development here? Oh, okay, intermediary maybe? Experts? Oh, wow. Okay, I'm impressed. Okay, now I have a lot of pressure. All right. So, yeah, so now you might be wondering, what the hell is Huff? Maybe you know a little bit about it. Maybe you already wrote some Huff contracts. Well, we are going to start with, the basics, with the definition that you can find on the website. So basically, Huff is a low-level programming language designed for developing highly optimized contracts that run on the EVM. So, well, since you guys are experts, you know exactly what this means. But maybe it would be a bit obscure or esoteric for some people. So we can have a look, a deeper look. So when it comes to smart contracts development, you have many different choices. You can use the most common ones like Solidity or Vyper. They're the usual languages that people are going to use. But there's a bit more to it. You can use, for example, inline assembly. So just adding some assembly like this, on top of your Solidity code. You can use a Solidity standalone assembly called Yule. You can use Huff. So we're going a bit deeper in the iceberg. And if you're a crazy person, you can write a mnemonic bytecode directly, but I wouldn't recommend it. So obviously, you guys know this is just a very simple Solidity smart contract, very basic. We just have one value. We can write this value, and then we can read this value. Pretty high level, very simple to understand. We have the equivalent in Vyper. Same thing, kind of high level. Then here we have something a bit more interesting. So here we're using inline assembly. So we are trying to dabble a little bit with the EVM. Pretty straightforward also, just some different ways to do things. This will be the complete assembly or Yule, so it's the standalone assembly version. So we have a bit more code, but things are still a bit simple. Then, yeah, if you want to have some fun, you have the mnemonic bytecode. So it's just all the instructions with some hexadecimal values. And this is just what the compiler will output. You can also write this by hand, but it might take some time. So now you might be wondering, why Huff? Why should we use Huff? Because we have many options. They seem to be quite reasonable. They seem to be quite flexible. We can do most of these things with them. Uniswap is written in Solidity. We have Curve in Vyper. We can do pretty much anything. Well, we have to go back a little bit into history, and basically Huff was created at first by the Aztec team. It was in 2018, and they were working on a smart contract called, bear with me, Wire Strudel. I don't know what this means, but that was the name of the contract, and basically just a elliptic curve, something similar to Zcash. And they wanted to write this in Solidity. They tried it, but the results were not convincing. They tried to use some assembly, but still it wasn't there. So they started to think about making some kind of way to be able to write assembly, but with extra function, extra features. And so this is how they came with the idea of writing Huff, of making Huff. So this is like I think the first Huff code ever written. So you can see it looks like a bit what we have now. Some stuff were removed. I think like like template, we don't have this anymore. But most of the things are still there up to this date. But when Aztec decided to create Huff, they had like very different intentions at what we have now. And like I think I took this quote from their README actually. So they said like Huff was designed with a complete disregard for semantics, safety, or basic consistency. So any similarities to production code are purely incidental, and Huff should on no account be used by anybody. So yeah, this is more or less what they said about Huff. They just wanted to build this tool for them, and the goal was not to really to spread it. It was open source, but it was not meant to be like shared. But what happened, so we know that obviously if you hear today, like the story and like the road that was like taken is quite big, and actually have evolved a lot since then. One day, like some guy decided to take the code and write like a new compiler in JavaScript, and some people decided to write then a new compiler in TypeScript, and more people came and they decided to write a brand new compiler in Rust, and then more people came and they said maybe it's time to write like a new compiler in Rust again, like from scratch. So we have like many different people, many different contributors. I just took this picture from GitHub. I think many of them are missing, but it's like maybe the main contributors that contributed to the core. Many other people contributed to other things like writing libraries or like making, I don't know, like writing articles or making presentations to Huff. But this is more or less like all the people that contributed. And this is what I showed you earlier in Solidity or in Vyper, and this is like the same code in Huff. So as you can see, it's not that big. It's maybe a bit scary, but we don't have much code actually. It's kind of simple. We are going to go through it in a bit, but first, let's answer this question. So like, really, why the hell should I use Huff? I think that's an honest question, and yeah, let's answer this question. So first, I think what's really nice when you're using Huff is that you have access to like all the opcodes. It's not the case when you're using inline assembly. Even if you're using like standalone assembly, you cannot choose like all the opcodes. You cannot like manipulate the stack, for example. You have like many restrictions. When you are using Huff, you have access to well, pretty much anything that you want. That's the first thing. Also, we've been talking about gas costs. So this chart might be, it's not very like precise. It's maybe a bit outdated. I took it 1 year ago, I think. Patrick Collins shared it on Twitter, so I just like been reusing it. But it gives you like an idea. Like this is like the we are comparing the cost to like create a contract, to deploy a contract. And here we're just like comparing the cost to read and write read and write operations, so using Huff, Vyper, Solidity, etc. So it's not exact, but it can give you like a rough idea of how we can optimize the code. Obviously, there are some stuff that are in the Solidity and Vyper code that we don't have, but yeah, more freedom. You can do whatever you want. If you want to remove many safety features, you can do it, so you can make your code like more optimized. So some very specific use cases, if you're into MEV, if you want to write bots, if you want to do like very specific smart contracts, you can use Huff because it will be like purely optimized to exactly what you want to do, and you can like reduce the gas costs like in an interesting way. Yeah, you can also do some crazy things, like this guy, for example, wrote Uniswap v2 in Huff, which is quite impressive, actually. I remember some people wanted like to deploy DEX that was purely written in Huff. I don't know if this ever happened, but that was like a crazy idea. We have this also, Huffidity, which is like a way to run Huff code inside of Solidity by injecting the code. Yeah, it's a bit esoteric, exotic, I don't know, you will call it the way you want, but this is like at the boundary of of what we can do, and maybe it's not a good idea to do this either. But I think like the best use case for Huff basically is just to teach you how the EVM works, so you can become the EVM Chad. Yeah, because what we have been seeing is that since Huff has been created or revived, we can say it this way, many people like me got interested into Huff, and we can learn a lot about the EVM, and then we can get more familiar with it and just become a better developer. So when you will be writing Solidity code, you know exactly like what the code is doing. You can maybe write some optimizations in inline assembly, or if you're debugging something. So it will give you like a better understanding of like how the EVM works, how under the hood everything is happening. And yeah, like today, I mean, it's been a while already, but I mean, like nowadays, there are many tools. Like for example, if you want to write some Huff, you can use like Foundry to test your contract. So it's extremely simple. There's a template for that. And then there are also like libraries like HuffMate. So if you want to write something, then I don't know, like an ERC20, there are already like a template that was made. But I think like the best use case for this library is to just go through all the contracts and try to understand how they work. I think it's like maybe has like all the same contract as Soulmate. Maybe, I'm not sure, but many stuff like Ownable, like many create tree libraries, stuff like that. So it's very impressive also. So yeah, I think now it's time. I made like a small introduction. So I think now it's time to maybe start going deeper into Huff. So I think we're going to do this in two parts actually. First, I'm just going to go through like all the features that we have in Rust, so you guys can get like a more like a better understanding of what we can do and how we can do it. And then we'll get to write some actual code. So yeah, as I said, basically like Huff is like some kind of assembly language with many convenient features. And yeah, first I'm just going to go through like how the EVM works. I'm sure like all of you know, but maybe there's like 1-2 people that are not very familiar with it. So I just want to be sure that we're all on the same page. So this is a stack. This is where most of the manipulations or handle, like if you want to store values, if you want to compute stuff, like everything will be happening into the stack. So the way it works is very simple. You have here like a pile. You're just like stacking values from like the top, the bottom to the top. So you're just like adding new values on top. If you want to remove a value, you will pop the last value that you just added. And what is going to happen is that, let's say we have like A, B, C, and D, and then you want to multiply something, so you're going to use the multiply opcode. Then what is going to happen is that the EVM is just going to take like the 2 latest values, and it will multiply them, and it's going to put them back into the stack. Yeah, this is just like another representation of the stack, so still the same thing. Just be aware we have like plenty of space, like 1024 values. The thing is that we can only get like the 32 first values because we have only like opcodes. For now, we only have opcodes to get value up to the 32nd value. This will change maybe with the EOF, but for now, this is the way things works. And this is why we have like a stack too deep in Solidity also. Then we have the memory, which is like another area to save some values. The memory is very simple. You have like an address and a value. Addresses and values, they are using like 32 bytes. So basically you can just store whatever you want, wherever you want. You just have to follow this pattern. the storage is following the same pattern, and we also have the transient storage, which is also more or less the same thing. And this is the call data. So call data, when we are referring to it, is just like a value that someone is passing to your contract when they're calling them. So this is a swap on Uniswap v2. Obviously, if you don't know, like, you might not know what are these numbers, but basically in your contract you're supposed to. So don't worry too much about that. But yeah, basically we can see like the first bytes, just the signature of the function. And then all the other values, like after all the zeros, these are just like values like amounts, for example, that are passed around, or maybe addresses. Yeah, just like a very cool website if you want to be or get more familiar with like how the EVM works. You can go on evm.codes. There are many different sections. The first one is like opcodes, which is this is what I showed you earlier, just like a list of all the opcodes. It's just explaining exactly how they work. It's like a very convenient. And then you have the playground, so you can write some Solidity code, Yule code, I think also like mnemonic bytecode, and then you can just hit the run button, and you can see like what's happening step by step into the memory, the stack, the storage, the transient storage, the return values. So it's extremely convenient, and it's a great resource just to use, like to learn how the EVM works. There's like a Huff fork for this, but might not be updated, so I'm not going to show it here. And yeah, I guess it's time to just go through like all the things we have in Huff. So first, like in Huff, you can like have we have the interface definition, which is something very similar to what we have in Solidity or Vyper or whatever. You can just like define functions, you can define events, you can define errors also. It's not there, but you can also do it. And then you just have to pass like some parameters. So this will be useful in two cases. Either to define like a function so people can call your smart contract, or if you want to call like another contract, let's say like an ERC20, then you can define the transfer function, and then you will use this definition later on to call the contract. We do have some built-in functions in Huff. So we have the function signature, the event hash, and the error function. These three functions works more or less the same way, and it's related to the interface definition. Once you define, let's say, for example, approve, and you want to call approve, then you will be able to use like function sig, and you put just approve inside of the parentheses, and it will give you the signature of the function, so you can call it. The same thing for the event. If you want to emit an event, or if you want to revert, then you can use that for the error and get the selector. We have also write pad, which is just like shifting a value from the left to the right. And then we have like table start and table size. Basically, it's like a way to write switch statements in Huff. We'll get to that in a bit, though. And yeah, this is what I showed you. Like at the top, we're just defining like two errors, panic error and error. Like that's very original. But yeah, then later on, we want to revert. And then what we are going to do, we can just do like underscore error, and then we just put the name of the error you want to use, and then this will add the selector inside of our code, and then we can just like in this case we are reverting with some parameters, so we can just like store these parameters inside of the memory, and then we just have to call the revert function. So another thing that we can define, actually, constants. So I think it's pretty straightforward. You have a number, you can just define like a number, so it's like 0x420. This is an hexadecimal value, but you can also define numbers using like decimal values. Most of the people do it this way. And then whenever you want to use the your constant, then you just have to put the name inside of some brackets, and then we'll just like input the right value. Then we have jump labels. So jump labels are defined within a macro or a function. We'll see what they are a bit later. But basically, it's very simple. You have just like a piece of code, like for example, success here. Success is just defined by this instruction. So like we store something and then we just return. And so what is going to happen if you look at the top? I think there's like a pointer. Yeah, if you look here, basically we are doing something here, and then we say, okay, we want to jump to the success. So we just have to call the label success, and we jump to it, and this piece of code will be executed. So it's quite straightforward also. You can also do it with jump E, so you can add like a condition to this jump. And then we have functions. So functions can have like arguments that you can pass here. And yeah, there is one weird thing here, so takes and returns. So this is something that can help you know what the function is expecting from the stack and what the function will left into the stack. So basically what is going to happen is that this function is expecting like 3 values in the stack, and after its execution, it will leave like 1 value into the stack. So as far as I know, this is not enforced by the compiler, but it's more like a way for you to just like know more or less what you should have, how you can manage the stack. And yeah, so basically functions. So we have functions and macros, and like the big difference is that functions, they are copied only once. The compiler is going to take the code of your function, and it's just going to put it at the end of all the bytecode. And whenever you're going to call a function, then in the execution of your code, it's going to jump to where the function is. And when the function has been executed, it's going to jump back and keep on with the execution of your code, which is different from macros. In the case of macros, what is going to happen? Every time you're going to invoke this macro, then the compiler is going to copy the old code and directly put it in your bytecode, what was compiled. So this means that if you're using like macros, then the size of your smart contract might be a bit larger, but it might be cheaper guys-wise because you will be like avoiding like jumping around back and forth. And also, by the way, yeah, so we don't have it here, but basically macros, they accept like parameters, and you have also the takes and returns indications. So we have like 2 important macros that you need to know. We have the constructor. It works the same way as Solidity actually. So basically, if you want to execute some code when you're deploying your contract, then you just have to put it into the constructor. And we have the main macro. The main macro is well, quite simple. This is like the entry point of your smart contract. So whenever someone is going to call your smart contract, the main macro will be executed. So this is where you want to do like the function dispatching or things like that. But we are going to see that in a minute. We have jump tables, so it's pretty small and a bit long. So yeah, it's just a way to do like switch statements in Huff. So maybe we can see that a bit later. So yeah, let's code. So I think it's time now to write some actual code. So yeah, we need, I hope like you guys all have a laptop, otherwise it's going to be a bit boring for you, I'm sorry. So we are going to write some code. We are going to use the template that is using Foundry. So if you don't have Foundry, you can install it using this command. I'll just give you like a few minutes to start installing stuff. So if you already have Foundry, you can install directly Huff. Like this is like the version manager, I would say. So you can run this. Maybe I should have put these two into the same slide. I'm sorry. Just tell me if you guys all have the first step done, then we can move forward. If you have any questions about Huff or about how to install things, you can just ask me now, I think. Yeah. Oh, shit. Which version do you have? Package? Okay, is this like the... Yeah, Huff Up should be like the... Okay, check your Wi-Fi. Because I know like the Wi-Fi is a bit long now. It's good. Oh shit. Try again maybe? Warning. That's pretty annoying. Yeah, I'm sorry. I'm not sure how to help you here. Yeah.
Just checking. Am I expecting any artifacts from this?
Let's see.
Like, I do get status. I can't see any type of output. I don't know if it's
What is the repo you opened?
I just made my own
Oh.
project and just added a macro.
Yeah, it's a bit weird. We're going to use Foundry, so it's just going to like do everything. But I think like the yeah, it should be working. Try try just like have C dash capital V, and then just to see if I mean it's saying compiling. So yeah, you have the right version. Yeah. Okay. I think if you want to output something, there is like a command. If you check, if you try help, it will tell you. Yeah. There is something like an output, bytecode, stuff like that. Yeah, it's a bit weird. No worries. All right, so if you guys have Foundry, we can move forward. Then you just need to install Huff, and once you've done this, you can install. So this is installing the package manager, not the package, sorry, the version manager. Then you can install the latest version, and this should be working. So you should get like Huff 0.3.2, something like that, and Forge, whatever. Like should be working, should be giving you like some outputs. Yep. This one. Let me see if I can give you like all the commands. That would be easier. It's not loading. All good? Yeah. You have Linux? Okay. Oh, it's still installing. Oh shit. Yeah, I hope it's not going to take too much time. Worst case scenario, like I still have some slides so I can show you guys, but it would be better if we can just like code along. Yeah, all good? Nice. Yeah, installing, downloading. Okay. All good over here? Yeah. Nice. It's Huff C. Nice. Perfect. All good. All right, installing. That's nice. All right, I'm just going to give you a few more minutes because I see many people still downloading. It takes a few minutes, I think, to install everything. Uh, did you? Oh, you built it? Okay. Oh, perfect. Nice. All good. All good here? Yeah? Okay. Do you guys need help or are you good? Good? Yeah, thank you. Okay. Yeah, you have like both versions. Everything is working? Ah, perfect. All right, yeah, let's move forward. Where's the clicker? Yeah, we're just going to be writing like two very simple contracts today. I don't know how much time it will take. Like we have 2 hours, but yeah, since you guys are experts, I'm joking, but like I feel like it will be pretty straightforward. So maybe it will not take like the whole time. Yeah, if you do Huff up, you do Huff C dash capital V forward dash capital V. If you have everything working here, then what you can do, you can clone this repo, just like a very basic template I've made using the actual Foundry template. So you should be able to clone this. I just hope it's public. So just let me know if it works. And when you have this, there will be like one extension. If you're in VS Code, there will be one extension that is suggested. It's called like a Huff language by Huff language. And it will just give you like a syntax, like colors, stuff like that. There is also debugger, but we're not going to use that today. So yeah, just let me know if like, okay, perfect, good. I'm relieved. Nice. It should be, so do you have VS Code? If you open the repo in VS Code, it should like pop up the suggested extension. Otherwise, it's called like Huff language, I think. You got it? Perfect. Yeah, it would be better to be using having some colors, otherwise it's going to be a bit hard just to see what we're doing. Yeah, I'll just give you a few minutes because I think the slide just after this, yeah, like after this we're just going to be cooking. So I just want to be sure that everyone can follow. It's the right extension that was.
Yes, I was trying to install an extension that the budget TPS only to send rough report.
Oh, you can just decline this.
Yes,
Nice.
but I think I'm right.
Yeah, perfect. Okay, good. Yeah, looks like we are all set. So what we are going to do, we are going to be writing our first Huff contract. So I think there might be a source folder. If maybe it's not there anymore, I don't know. But you can just make like a src folder, and then you can write the first, like create the first file. You can name it the way you want, compute.huff, or whatever you want, and then we are going to be writing some code. So this is the first contract we are going to be writing today. It's extremely complicated, you will see. This contract is just going to take two values and multiply, no, not multiply actually, add these values together and then just going to return them. So as you can see, it's extremely hard to understand. Yes, so let's just like follow along. If you guys have your setup already, you can code at the same time. So the first thing we want to do is that we are just going to define a function. So here, as you can see, this is what we're doing here. Let's call it, I don't like compute. You can call it add or whatever. It doesn't really matter. So this function is going to accept two parameters. So we need like one uint 256 and why not another uint 256. And then it's going to return, well, something very original, one uint 256. So this is just like the function that we define, and this definition will be used by us inside of our Huff contract, but it will also be used by the people that want to interact with our contracts. So then we have this, which is a macro here that we are calling compute. So we can define this macro here. Just a way to organize our code. It will be also, another way would be just to shove everything into the main macro, but that's, no, we are like educated people, so we are not going to do that. I'm going to go through what's in there in a second, but first I want to talk about the main macro, which is just here. So as I said earlier, the main macro is the first thing that is going to be called when someone is calling your contract. This is like the entry. So in our case, it's pretty simple. So let's go through it. So okay, you guys can. So maybe you're writing at the same time. So I will slow down. I'm sorry. So yeah, first I think the easiest thing is just to write the first function definition on top, and then you can go directly to this. Don't write this so now, we'll do it just after. Yes. Yeah. Here? Oh. Yes, yes. So why are we returning nothing here? We are not like leaving anything in the stack. It's because we are returning here, and this return is actually the end of the call. So when we are returning something in Huff, we are actually like returning values from the call. So it's like the end of the call. I know it's a bit the names may be a bit confusing, right? Yeah, because we have returns which is not actually returning but just leaving stuff in the stack. So that's true that it can be a bit confusing. So yeah, I'll just are you guys ready or not to go through the main macro? All right. Okay, let's go. So now we are going to do what we are calling like function dispatching. We have like a very basic implementation, but it works the exact same way. For example, in Solidity or Vyper, there are many different ways to do this, but this is like the most common way. So basically, what is going to happen is that someone is going to call our smart contract. They will send us some call data, and we just want to know, okay, what do they want to do? Like, what is going to happen? So what we are going to do is very simple. We say we want to load the call data, so all the values that were given to us, but we want to load it starting from like the first byte. We want to load it from the start. And then maybe you know this or maybe you don't know, but basically like function signatures, they only have like 4 bytes. So how does it work when someone is calling a contract in Solidity or like in the EVM? Like the standard is that when you're calling a smart contract, the first bytes, the 4 first bytes are the function selector. So what you are going to do is that when you receive the call data, you are like, okay, I want to know which function we should call inside of our contract. So I'm going to check in the call data what the guy wanted me to call. So we are going to load the whole call data here, and this like magic number, the value is like 2024 bits. So it's like 28 bytes. And so what is going to happen here? We put in the stack like the whole call data. So we have everything, and then we say we want to move to the right, like all the call data. So we are going to move everything to the right, but we are moving to 28 bytes. So we are going to leave a value which is only, well, you can do like 32 bytes minus 28, and you have 4 bytes. So this is like the function selector. And so, yeah, we have a function selector. So we know which function the sender wants to call. But now we need to check, okay, so do we have this function? Maybe we don't have it, maybe it's a mistake. So what is going to happen here? We are going to do exactly like the function dispatching. So we are going to load here our function signature. So this is what we have. Compute, it's here. This is what we define, and this is what we are expecting. And then we're going to do like equals. So equal here is going to check if what we loaded here, what we sliced from the call data, the function signature, function selector we have, is equal to this one, the function signature that we are expecting. And then we say, okay, so if it's equal, then we'll have a 0 here. We'll have a 1. If it's not equal, we have a 0. And then we are just going to call the jump if opcode, and the jump if opcode is very simple. If this is 0, then we are just going to continue. If this is 1, we are going to jump to here, compute, the jump label I showed you. I explained to you this earlier. So maybe this is a bit confusing. Just let me know if we need to slow down. Okay, you have a question. Go ahead.
On the function signature, what is it doing exactly there? On the function signature, how is that? Could you explain, dive deeper into that?
Yeah, sure. So basically, this is the same thing as Solidity when you have like encoding something, or if you define a function in Solidity, you can get like the signature, you can get like the 4 bytes. And this is the same thing here. We define this function here. Like this is like our function.
Oh,
and
I see. So it's
when
actually
you're
computing the signature, function signature from the compute.
Exactly.
Function.
It's computing the hash.
Got it.
So the hash of this, and then it's just going to slice and only get the 4 first bytes.
Okay. Could you go back a little bit on the call data piece? So is it just leaving on the stack the 4 bytes of the function signature?
So basically here we are going to, it's a bit weird because like, you have to add the value on the stack and then you call the instruction. So it's a bit hard to explain because I need to explain like back and forth what the values are. But basically you're like, I want to, from the start, I want to load the call data. So you will be loading the call data from the first byte, from the byte 0. But you are going like to load 32 bytes. What is going to happen is that this function is going to take like a slice of 32 bytes and put it into the stack. So you will have 4 bytes for the function signature, but then you will have 28 bytes, which will be like nonsense.
The parameters.
Yeah, it will be, in our case, it won't be nonsense, but it will be this, the first parameter, but it won't even be like the whole parameter because this is like 32 bytes. So yeah, maybe I should have put like a graph or something. It's hard to explain this just like this, but
Yeah, it would be helpful if you had like the stack on the right hand side.
good idea. I'll
to
see if
visualize.
I can do something. I'll see if I can do something actually after. But yeah, basically the idea is that you're loading here 32 bytes of call data starting at the position 0. But in this case, we only want the first 4 bytes. So we say, okay, let's just move to the right this element in the stack, and we want to move it to 28 bytes. So we move it like this, and so we are left with 4 bytes, which is the function signature.
So on the stack, all that's left from the call data is the first 4 bytes, which is the function signature.
Exactly.
Got it.
And after we just check, okay, is this like a valid function signature? Because someone can just be like spamming our contract. So we need to do like a proper check. Which function do they want to call? So we are going, we are going to use, we are going to load our own function signature, what we define here, into the stack. So basically the stack we will be their function signature, our function signature on top, and then we'll just do like equal, and both values will be removed, and equal will just leave a 0 if they are not equal, if they are not like the same, and it would put a 1 if like both signatures are the same. I just want to, there is like here, duplicate 1. This is not needed here, so I'm not going to talk about it. We'll see that after, but this is not needed here, so don't worry about it. And yeah, so we are checking here, and yeah, like the final thing to do is just to jump accordingly. If the function signature is valid, if we have something that we are expecting, then we jump here to compute. And in our case, we decided to make things the proper way, so we define like a macro for compute. The other solution would be just to shove all the code here, but it's just cleaner to do it here. And yeah, if they don't have like a valid function signature, we're just going to revert. We don't care. They don't. They're not like asking for the right function, so we are not like reverting with any extra data. We're just returning 0 value, just reverting the transaction. But we could have been like reverting and say like anything you want, like wrong function signature or whatever. All right, do you have any questions? Yes, I'll give you the mic.
I see by the looks of the function and the main functions, you have a revert and return. It's all recursive inside of the EVM, or it's just for showing they have a revert or return function?
This or opcodes?
Yeah, I refer this, the EVM is recursive when the codes.
Oh, do you mean like, is this going like to fail the whole transaction, or?
Continue the transaction, the execution, until you put the return on the revert, or revert.
Yeah, if you revert here, I mean, it's the same thing in Solidity. You can revert here, but then the call can continue. It's the same.
Continue infinitely until the gas.
Oh, no, sorry. Okay, I understand it not the right way. This is the end of the transaction, but it will continue if there are like more things after. Other opcodes to execute, but if you reach like the end, like in this case we are reverting, but it depends on like well how you're writing your contract and who is calling your contract, because like if you I don't know like I mean it depends. I don't know exactly how to answer this, but yeah, like basically it will consume gas, but if you reach the end of the call, then it will just stop consuming gas. You know?
Okay.
Because it's only consuming gas when it's like executing operations, but if there is nothing left to execute, then the transaction will just stop.
Okay, so if I remove the return or the revert, it just stops completely.
If you do that, if you remove the return here, I'm not sure what it will do actually. That's a good question. I think we'll stop because this is here actually in like the code. This will be compiled at the end of our contract, and then if you do this, then after the contract has ended, so I think it will just stop. But otherwise, you can, if you forgot something, you can make a loop. If you put like here something, then it will jump here and go here and jump here. Like it will be a loop. It will consume all the gas and just revert with out of gas, actually.
Okay, perfect. Thank you.
Question about the 0x00 call data load.
Yes.
There. So that sounds a bit heavy. Is that the most efficient way of getting extracting the selector?
Mm-hmm.
Okay, cool.
Yeah, because you can, when you're using like call data load, you can only load like 32 bytes. You're loading like a whole piece of information into the stack. Then you have to move forward to get the actual function selector. There is another way actually, and I think you can load like a single byte from the call data, but that is not standard. So you can do it, but it's not like the standard way. So you could be like loading, I don't know, like the first, you say, okay, this is like 1, and if this is 1, we compute, or we go to something that will add. If this is 2, then we can go to something that will do minus, subtract, things like that. But the standard way is like 4 bytes. Yes, so we can continue. So basically, once you once you are going to compare here, and then you have, like, as I said, like 2 different cases, 2 different scenarios. Either you can revert, so we are just reverting like the hard way. Or we might be going to our macro here. And the macro is kind of simple. So we know that we have like 2 uwins 256 that we need to have into the stack because we want to add them together and return the sum of these 2 values. So we are going to do the exact same thing as we did here. Call the same function. And so in this case, we know that the 4 first bytes are the function signature. So we are going to ignore them. And we say, okay, put into the stack, so call data load, but put into the stack the call data starting at the bytes 4. So ignore the first 4 bytes and then put the call data. So this will take 32 bytes of call data and put it into the stack. Then we just have to compute, and we say, okay, we already loaded 4 bytes for the function signature. We already loaded 32 bytes for the first parameter, the first uint 256. Then it looks like it could be 36 bytes that we already loaded. So here's the value, 36. So we are going to say, okay, you have to load into the stack the next value, which is located after 36 bytes. So am I clear? I know this is a bit a bit heavy. If you have any question, feel free to ask them. I don't want to lose anyone, or maybe I already lost some of you. I don't know.
So back to the first couple of lines inside main.
Here.
So I get that we're putting the function signature on the stack.
Yep.
And then, so at the end of the second line, is that if it's equal, then compute jump, or does it say if it's equal compute? I guess I'm getting confused a little bit on the naming conventions, and like you've got, you know, you're defining function compute, and then you also have a label compute, and so
don't worry, I'll explain. So basically, okay, I understand what you mean. Okay, so the naming was maybe a bit wrong, but basically here compute we have our function, and this is only related to this. This and this are related. That's it. And then this compute is the jump label that we are defining here. So these 2 are related, but that's it. There are no other relationship. And so.
Okay, so, sorry, one
Yeah.
final thing on that. So
Go ahead.
where it's doing the equals, does it know automatically to just pick the first one off the stack and then compare it to
Yeah.
function and signature compute?
So because here we loaded like the function signature from the call data, so we have like at the top of the stack we have one function signature, the one that the sender gave us, and then here we are putting into the stack our own function signature. So when we are calling equal, it will say, okay, I need two elements from the stack, two values from the stack, and we'll just take like the two first values, which are the values we need. And then, so we have into the stack like either 1 or 0, and we say, okay, we might want to go to the compute jump label, which is here, and then we say, okay, go for it, but only if we have a 1. If you have a 0, then keep on reading the next code. So it will just keep on reading the next code, which is just like reverting. And revert just say, okay, I want to revert. Do you want to return some values from the memory? But we say, yeah, return zero value from the memory. That's it. The return here is very, very simple. More questions? Yes. Yeah, basically, yeah. And so this is like the most, I think, convenient thing when you are like writing stuff like this, because if you want to try to write like mnemonic bytecode, basically you can write all of this without Huff, but instead of having like compute here and here, instead of having something that you can read, you will have to put like a value, and this value will be like a location inside of your code. So you will say, for example, I want to go to like in my code to the location 148. But if you add more code here, then you have to change this value, you know. So this is just for us to be able to do this like in a convenient way. Yeah, so we are jumping to compute, and as I told you, just like a macro, so it's very, very simple in this case. We are loading our two values here. We know that we have to avoid the first 4 bytes, so this is like the next 32 bytes. This is the next 32 bytes after the first 36 bytes. And what is going to happen is that we have value A and value B inside of the stack. So we just have to call add, and add is exactly what I showed you earlier. So it just like with multiply, just taking like two values from the stack, it will add them together, and boom, they are put back into the stack. And what is going to happen here is that it's pretty simple. You'll see we have one value into the stack, and well, now we want to return it because we did all of this, but now we need to return our value. So return here is very simple. You can only return stuff from the memory. So we have to put our result, the sum that we just computed, into the memory. It's very simple. We are going to use the mstore opcode, and mstore takes one value here and one location inside of the memory, and then we just call mstore. So what we've done here is that we are putting here at the location 0 the value of add. So the value of add can be anything up to 32 bytes, obviously, but it can be anything. And yeah, we have like value in the memory. Yes. Wait for the mic. Sorry.
Isn't there a cost for putting that value in memory? I mean, it's not like...
Yeah, obviously.
Yeah, but why not return it from the stack?
Because it's not possible.
It's not possible.
Yeah, the way you can see, like I'll show you. Okay, let me just go back a little bit. We are. Oh, okay, we are here. So basically, you can see like we don't have the return function here, obviously. Okay, but if you go on this website, it's EVM.code. You will see like all the opcodes are explained here, and you will see like stack input. So basically, this is like when I was talking about the stack, this is like what is expected, and this is what will be left into the stack. So in our case, we are taking like A and B, and we are adding them. So we go from two elements to one element into the stack. And you can see like there is a description here. And if you go down, let me share my screen actually, because this is like an interesting question. Can you, yay. All right, let me see, EVM. All right, so if you go down here, I'm not going to take like too much time on this, but basically, yeah, let's do a research mstore here. You can see like, this is explaining how mstore works, and if you go to return, you will see like the explanation. It will just tell you, okay, stack input. So the definition is like the offset and the size. So basically, this means that we need to tell where we want to load the value from. So obviously inside of the memory and the size. That's it. So if you can you go back to the presentation? Thank you. Perfect. Yeah, so it's just how it works. We don't have a choice in this case. But I just wanted to show you the website, because it's going to explain to you exactly like all the opcodes work actually. It's pretty interesting. And even if you are not doing like going to do like some crazy things with Huff, if you just use like EVM.code and this and Huff, then you can just learn and have some fun understanding how things work. It's still quite interesting. Oops, I went way too far. Yeah, no, wait. This is the second one. This is the test.
That's the one.
Yeah, that's the right one. So yeah, and then we have yeah, as I just said, like return. So return is expecting two values. So we have the first value, which is the size of what we want to return. So in our case, it's 32 bytes. So it's like 0x20 in hexadecimal. You will see like many Huff code are written, like all the values are in hexadecimal. I guess because it's cooler, I don't know, but it's like more by convention. So you know that you want to return a uint 256, so you have to return 32 bytes. And this is the location in memory. You can see we just stored it here at the 0, like like madmans. And so we can just like call return, and that's it. We have our whole contract. So if you guys have the code ready, you can try writing a test actually. So this is how tests are working with Foundry and Huff. So we have something called like a Huff deployer, and this is pretty convenient because it's going to take your contract, compile it for you, and then you can just deploy it. So if you're familiar with Foundry, you will see it's the exact same experience as writing regular tests. Very easy, very simple, very convenient. The only small difference, I think there might be a better way to do this, but we'll do it like this today. We just need to redefine our interface here. So we say this is our contract compute, and then we just like copy paste what we defined here. We just need to put it again here in an interface. I think there's a better way to do it, but I'm not going to show it today because, yeah, we might be running out of time. So yeah, this is quite straightforward. You make like a new test file, then you just have to put like compute test, is test, whatever. Just like storage value for your contract. And then what is going to happen is that you just have to cast it. So we define the interface here. So you just cast it, or you can keep the address as you want. And then you're just going to use the Huff deployer, and you do like that. Sorry, you do like that deploy, and you put the name of your contract. I think the name of the contract is actually the name of the file. Yeah. So if you do this, the contract will be deployed, and then you can write your first test. So in this case, we're just like expecting random values that would be fuzzed. And yeah, we say, okay, so the contract should return C, and we can just check that C is the sum of A and B. I'll give you a few seconds. Do you have any questions or anything like that you're struggling with? Like I know this is a lot of things all at once. It can be a bit tedious to set up everything. So if something is not working, we still have like less than 1 hour, but we can take some time to fix some issues.
Can you just explain the math a little bit? Obviously, you've got unchecked there, so all of these UINT 256s can wrap.
Yeah.
And yeah, just explain the bounds on the. Is it just?
Yes. So I'm just doing here unchecked because if we go here in our, I'll go back to the next slide. I'm sorry for those who are copying the code. But if you go here like add, we have no overflow check. So if we are just doing like assert like the sum here, and we don't have unchecked, then Solidity will do like a overflow check, and then the code will revert, or we won't have the same result as our Huff code. But yeah, that's an interesting question, because here in Solidity now we have the overflow check, but we don't have it in Huff. So maybe like something that you guys can do is a way to prevent the Huff contract from the sum from overflowing. So that could be an interesting exercise. I think there's already a like a small library in HuffMate that can allow you to do this, but it could be quite simple to code actually.
Hey, sorry, one more question.
Where
you
are
mentioned
you?
that
Oh,
over
yeah.
here. Bit off topic, but you mentioned that advantage of using Huff is you have complete access to all the opcodes.
Yes.
What is one use case that you've found where you can particularly exploit that to achieve something that you haven't been able to do in another language? So personally, I haven't been coding for production things. I was more, as I said, like in the beginning, I really wanted to learn how the EVM was working, and actually just like writing some Huff was like the best way, because writing resources is a bit tedious. But otherwise, like I've seen many people doing like MEV boats or things like that. They're using Huff, and yeah, I mean like you have more. You have access to many things, and what is interesting also is that you're not writing Solidity code, you're not writing like or even Vyper, so you can do like as we saw earlier, like the function dispatching. If you are just writing your own bot for your own purpose, you don't care about that. So you can remove like a lot of the safety features from Solidity, because if you know exactly what you want to do, you can achieve it this way. But yeah, like some stuff also in like main differences. Also, you have access to more opcodes. I don't have like an exact example here, but I would say yeah, like there are so many other cases. But for this one specifically, I'm sure we can find it, but I don't have it in mind. Yeah. 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 Could be an example, yeah. All right. So, yep. Okay, let me see. Oh, you put like you went 8. Yeah, just put like 256. Yeah. Yes. Yeah, I think, yeah, if you have like compilation failed, I think there is one step that we haven't been doing yet, and it's just installing the packages. So if you have this, obviously if you have the first contract and then you have this, then you can try, just be sure to have everything installed. So you can just run like forge install, because now you might not have the Huff deployer module or whatever it's called. And then if you run like forge test, it should be working, I hope so. I tried it on my machine. Same thing, like here, you went 8. The result should just use like 256. Yeah, let's see if it works. I hope it will work. Oh,
Oh yeah, it's because they have a. I have an idea. I have an idea. I'm gonna put 8 now. I'm gonna put 8.
all right, let me know if it's working. Yeah, the test is passing. Hell yeah, yeah. You have the mic.
Is there a way to write the half codes like inline in Solidity?
Yeah,
Like-
actually,
like-
there is one. This is something I showed earlier. Like there is something called Huffidity. I guess it's called this way. But this is very, very experimental, and like this is leading to many. Where is this? It's here. Yeah, so it works, but I don't think this should ever be used in production, because like the way it works is that it's just injecting, it's compiling your code, it's injecting your code. So I think I mean, if you if you really want to use Huff for something in production, I guess like something interesting would be just to have like a deploy maybe a library or a contract. So I don't like some kind of precompiled. Just make a contract that is computing something. You deploy it, and then you can call from Solidity. You can call this contract. But yeah, like this is highly experimental. It hasn't been updated in a year, so I think it was more made for fun than something else. So are all the tests passing? No? You forgot the unchecked. Sorry, I just I just saw this. Yeah, if you, because so basically you had the exact issue that I was explaining. So like here, if you don't put the uncheck, then the test will revert, because adding these values will cause an overflow, and we still have like overflow checks in the test. Any issues? Okay. All right. So we covered the first contract. Yeah, I have another one if you guys are interested in. We still have 45 minutes if you want to suffer a little bit more. A failing test? Okay, let's see. Okay, did you put the unchecked?
Yes.
Oh, shit. Yeah. That's okay. Let me. Okay, the code. I think the Huff code looks great.
I don't know. Actually, it's just naming convention if you do it like this in Foundry, right? So it
Yeah,
shouldn't be
it,
any different.
yeah. It doesn't matter. Yeah, that's unfortunate. Okay, if the tests are failing, you can still check if you open on you can open this like URL in your browser, and you can check, or you can change the branch directly. I've made another branch called finish, and you should have the first test. This one, I mean the contract and the test. I hope they will work. But if they don't work, maybe there's a bug in my code. I don't know. So if you can find it, then that would be amazing. But maybe I made a mistake somewhere. Yeah, so it's passing. So what I'm thinking now, maybe, I don't know, maybe some values. Yeah, you found it? That's really funny. Do you yes? Yeah, when you're returning something.
Yeah, but like, what if what if it's in the stack? Like, suppose there's an add operation happening on these two values, right, which
Yeah.
are in the stack, and instead of doing M store, like you also mentioned that if there are two values in the stack, and if I perform an operation on the top two values, then those values get replaced by the result
Yeah.
speed, right? So the result is in the stack now.
Yeah.
Can't we return directly from the stack instead of like store, like the question we asked?
You cannot return from the stack. You need to put into memory. This is the way return works. Return can only read from the memory. This one? Yes.
I think there's something wrong with the installation, so I cannot find the file.
Oh.
But I did like force install,
Force install?
build, and then force test.
Where is your? Try to rename this to source SRC. Yeah, here. If you put contracts, I think it won't work. It's just naming conventions. Try this and let me know. Yes. Compute is the name of your file. Yeah. Yeah, yeah. Yeah, actually, I think I know. Maybe it works? Okay, perfect. Okay, let's see. What's the issue now? Counter example. That's funny. Okay, go back to the file, Huff. Yeah, let me see.
This capitalized, I think this is capitalized here.
Yeah, no, the problem is in the code now. Let me see. Call data, you're loading the right call. Oh, you forgot add. After call data. No, before. Yeah. Nice. All right. Any issues? Still failing? Oh gosh. Yeah. What was the issue? No compilation. Try to do like yeah. Try to run. Do like force test -- force. Oh shit! What? Oh shit! It's.
Okay, 1 second. Let me just like assert, remove, assert equal. What? Okay, it's not reverting here then, right?
That's weird. Why is he running a test if you don't have a test? Oh, it says revert.
Yeah, like I think it's reverting here now.
Oh.
C1, you jump to complement.
Yeah, I'm not sure exactly. Check on the other branch. You can switch the branch. Go to the finish branch if you want. Yeah, if it doesn't work after, I can look into. But I think we are going to move forward because I feel like you guys have the code working. So yeah, we still have like 40 minutes. So maybe we can go through another contract. Yes, so this one is more or less the same thing. No, it's not exactly the same thing, but we are going to cover one extra opcode. So now, in this case, what we want to do is that you will see it's very simple. We just want to be able to get a value from the sender and store this value. And if the sender wants to read this value, then we are just going to return it. So once again, very, very basic contract, but this will allow us to cover a few different things. So in this case, well, we are going to start by the interface definition once again. So we are going to define two values. The first value is just two functions, sorry. And the first function is just set value. So in this case, we want, well, u into 56, which is very original. And then we're just going to make like another function called get value. And in this case, we don't want to set something, but we want to return something. And then we are going to cover something else. So we are going to make a new constant called value location. And so we are going to use this, which is like some kind of built-in function that we haven't seen yet, called free storage pointer. And basically what this function does, it's very simple. It's just going to give you a location where the storage is free. So in this case, if we call it now, it will be 0 because the first location that is free is located at index 0. Very simple. If you call it again, it will be 1 because we have this value already taking the first slot, so the slot 0, and then after we can take the slot 0, 1, 2, etc. Any questions? No? All right. And then we are going to go directly to the main entry point. So this is going to be almost the same code as we did actually. So we are loading the call data from the start. We are shifting to the right 28 bytes. And what is going to happen here is that I told you earlier that we don't care about the duplicate one, the dup one, but in this case we need it because what is going to happen here that here we have the function signature that we received from the sender in the stack. And we want to keep it for later. So we are going to duplicate it. So what is going to happen is that we will have 2 times the function signature we received from the sender. Then we're just going to be doing exactly what we did earlier. So we are going to load, for example, the first set value, the signature of the set value function. So we want to check, okay, maybe the sender, they want to set the value. Okay, let's see. So yeah, we load the set value function signature and we do equal. And yeah, maybe it's equal, maybe it's not, we don't know. So we said, okay, you can jump to set if the value that we just received is equal to set value, and then you know the drill. It will go here and then to the macro set value, and it will go here. But if it's not the case, then what is going to happen is that, well, Jumpy is just going to do nothing, and so we will go back here. And in this case also, dump one here, like dump one, sorry, is not needed, but yeah, don't worry about it. But this means that here, when we called equal, we consume the first value that we loaded here, and we consume this value too. So luckily, we duplicated this value into the stack. So this means that we have value A, 2 times the value A, then the value B, and then they are consumed. So we are left with the value A. So then we can load the function signature of get value, and then we have the value A and the signature of get value, and then we can do the same thing again, equal, and if it's equal, we can jump to the get macro, and so we go here, and then whoop, we execute it here. It is clear or not? No? I'm sorry. Do you maybe you have a question and you can answer, like you have a specific point that you don't understand, and maybe I can explain it like in a different way. Can we have a mic over here, please?
Thank you, Clement. So dup1, is that duplicating the...
Yes.
Okay, it is duplicating the stack.
Exactly. The dup1 is duplicating the first item of the stack.
On the stack. So
yeah,
it's duplicating the call, the function signature.
of the sender, yeah. So
Of the
it's
sender.
duplicating the function signature that we received. And so basically, the dup1 here is just a way for us to avoid doing this again.
Okay.
Because we could be doing this, and then we do this, we don't duplicate. But if it's not like, if the sender is not willing to execute set value, then, well, we have to check if they want to execute get value. So we need the function signature again. So we could be doing this again, but it will be costly. It will cost
Okay. So
a lot
then,
of gas.
don't you have the function signature on the stack 3 times? Because you called duplicate 1 twice.
Yeah, this one is an error.
Oh, okay.
I'm
Okay.
sorry about
all right,
that.
all right,
This
all right.
one is an error because I just like copy pasted that
Got
line,
it.
and
Okay.
then I changed it.
I mean, there's no harm because you're not doing anything after that.
Exactly,
But you
exactly.
do have the function signatures.
This could be
on it.
leading to some issues. In our case, we are just reverting right after, so it doesn't matter. But I can show you after, like, for example, in the case of ERC20 or something like that. But yeah, you can have like many different things, so you will duplicate every time. But on the last time, it's not needed. You're right.
Okay, all right, that makes sense. So, a question. So when you do the equals, it's
Yes.
actually taking 2 values that's on the stack. Well,
Yes.
no, well, taking one value that's already on the stack, and the other value is the one that's computed as part of that call.
It's taking, like, when you're doing equal is going to take, so this, so we have this value in the stack.
Right, that's on the stack, and then
So you can imagine that here we duplicate, so this means that this value is here. It's like we are cloning it, and
Clement,
equal.
if you don't mind, I'm just going to interrupt you really quick because
Yeah.
the question I have is the function signature that looks like a macro. Is that putting the value of that? It's computing the function signature of get value, right? And is it putting it on the stack, and then the equal function is computing the equal between those 2 values that are on the
Yeah.
stack? Okay, thank you.
Because so this is exactly what you said. Here, equal is going to take the first element of the stack and the second element of the stack. So that was duplicated from this. So we have like here our stuff that was computed and added to the stack, and then the stuff we just computed ourselves.
Perfect, thank you.
Yeah, and then it's kind of simple here, like to set the value. Well, we just go to the macro here, set value, and well, this is exactly what we've been doing earlier. We know that we need to avoid the first 4 bytes because this is the function signature, so we don't really care about it. So we just do, okay, we want to load 32 bytes starting after the 4 bytes. And then we are going to use a different opcode that we never used called store. So you can see like previously we've been using mstore, which is very well, explicit memory store. And in this case, we want to store in the storage because the user is setting a value. So we want to keep it for a long time. So we are going to call store, and store works in a very similar way to mstore. It takes like one location and one value. And so what we are doing here in this case, I showed you this earlier when we talked about constants. We are just going to use like within brackets, we are going to call value location, which was defined by free storage pointer, which should be 0. So this means that we want to store in the storage at this location the value that is starting at the call data after the first 4 bytes. So kind of simple, it's just weird that, I think the weirdest thing here is that you are just doing things in reverse. You have to put element in the stack, and then you have to call a function that will take all the elements in the opposite direction. So it's a bit weird to think that way, but you get used to it. And yeah, like you mentioned like many times like the stack, how it works. And so like a convention some people are doing, and actually I think there's a tool for that. Some people here like add comments, and within the brackets they just put what is in the stack. So they will say, okay, here we have a value here. So because we loaded this value, and then they say we have a pointer here. So the stack is like the pointer and the value, and they say, okay, we are calling storage store, so it's going to use 2 values, so then the stack is empty. So it's like also a nice way to be able to track what you're actually doing.
Question?
Yep.
So on the stack, what is the first argument? Is it the one at the topmost, and then the second argument is the one below it?
Yes.
Okay,
so when you're calling
order.
a function, it will take like the one at the top, and it will go like it will remove them one by one. So it will always take what is on top.
Okay, so the topmost one is the first argument in the function signature, and then the second.
In this case, I would first use like the function signature. So if you are doing like minus, you will do this minus this. So this function, this macro, sorry, is kind of simple. And then I think there might be an issue actually with the code. Yeah, okay, let's see how it works. I wrote this. The test was passing actually, but I think there might be an issue from what you were saying earlier. So let's see. Then the get value macro is kind of similar to what we've been doing, but yeah, we're just going to use like a new opcode called storage load, and it's very simple. You just say I want to load into the stack. I want to load I want to load into the stack the value that is stored at this location. So we're just going to use our value location constant here. We put it into the brackets, and then we just say, yeah, I want to load this value, and the value will be put into the stack. And then same thing as before, we put this value at the position 0 into the memory, and then we call return, and we say, you can return 32 bytes starting at the position 0 from the memory, and it will return the value. So kind of straightforward, yeah.
Just a different kind of question here. If there's a smart contract that's been deployed, but the code was not published, can you decompile it into Huff?
I think there's a decompiler, yeah. I'm not sure if it's really powerful, but I think there's one, yeah.
There's one. Because I was just thinking in terms of reverse engineering the smart contract, right?
You can use it actually. Yeah, that's pretty nice. and more convenient than reading the bytecode directly. Yes, so I think that's it for this contract. It's kind of straightforward. We already saw like the function dispatching and like to store into the storage or to load from the storage. It's very simple. Yeah. Do you have any questions so far? Yeah. You put a stop. I'm not sure. Yeah, I think it's needed. I'm not sure if it's needed or not. Okay, let's see. You can check with the other branch. Go to the finish branch. Code is the same. Okay, I'll let you check and I'll be back after. Any extra questions? Yes.
How does Huff compare to YOL?
Well, I think like, well, the main difference is that, as we were saying like earlier, you have more power in the sense that even in YOL you cannot manipulate the stack. I think there are a few things that you cannot do. In Huff, you can like you can like duplicate elements in the stack. You can like swap them. Yeah, you're free to do whatever you want. So you can do like more optimized things. I would say that's about it. But yeah, I guess it also depends on the use cases. But yeah, I'm not aware of many contracts that were written in pure YOL. But yeah, if you're using like YOL, like inline assembly in Solidity, then I mean the obvious reason would be just to be optimizing very small portions, snippets of code. If you want to, yeah. So this is the test for the contract that we just wrote. So still very simple, straightforward. We are also using the Huff deployer, and yeah, I added some console log just for the sake of it, but basically still quite straightforward. I'll just give you a few minutes if you want to write the test and try out. Oh, you had this? Oh, you don't need it. Yeah, obviously. Yeah, I'm a bit confused. Are you running the... Oh, but you are running the test from counter, and then you're checking maybe the other tests. Okay. All good? Yeah, just let me know if the tests are passing or if you're having any issues. How is it going? All good? It's oh, you added more things? Yeah. Nice. Okay, cool. All right. Yeah, that's. I don't have another contract after that, so if you want to, we can just be like talking if you have more questions, or if you want to, I don't know, add something else into the code and you want me to let you know how we could work, feel free to, yep.
มีคำถามออนไลน์บ้างไหมครับในออนไลน์มีขึ้นไหมอ๋อเนี่ยอ๋อมันเป็นของในห้องใช่ไหมงั้นก็เดี๋ยวก็จบละซื้อมา
What's the issue now? Failing assertion failed. Value, increment value. What is doing increment? Yeah. Oh, okay, you want to, oh, I see, nice, okay, cool. So yeah, you're loading the call data, then you are loading, it's good actually, it should be working, it's,
putting it back to the storage.
yeah. To be honest, try adding like a return. I think that might be the issue, I'm not sure. Here we're not adding it. Yeah, I'm just. I think we might need it. Yeah, I'll copy paste the just return nothing just to see. This will return something. So just. So what you need, for example, if you put like 0, 0 return, it would just end the transaction. So you don't have to return something. You can just like put this to return the transaction. To stop the transaction. And if are you familiar with Foundry? Read. Okay. Oh, it works. Perfect. Okay, that was it. Nice. Okay, all good. Yeah, if the tests are failing, you might want to add here. I think it would be better, especially if you change the code. Here, you can do like you can add after that line return. So like this, but instead of having like 20 here, you can just like put 0, 0 return. So here you can just like return nothing. So this will just let know that after calling this macro, then you just have to end the transaction. Because otherwise, what could happen is that set value is executed, and then you go here to the jump label, and then get value is executed also. So you have some weird scenarios. So I think it would be just better to do like add return here. Just return nothing. Just 0, 0 return. This should fix things. If you have this, it's not working, try to do what I just said.
Yeah.
In your function, just like return nothing.
Yeah.
Because it fixed the issue for the for him. Yep.
Also, another thing you can do is you can just do stop.
Yeah, stop also works, but I'm not sure about the gas cost.
You can just stop.
Yeah, you can stop also, but I'm not sure about the gas cost. We should check because sometimes stop is just like consuming the rest of the gas or things like that. So, you can just research and see like alt execution. Oh yeah. You can, if you click here, you have more details. Yeah, successfully. Yeah, you can. Yeah, it works. You can also add stop. Yeah, that's another way to just end the execution of the macro safely. Yeah, sure.
How does the function sig know which set value you're referring to if you have multiple with different arguments? If you have multiple set value with taking different number of arguments?
Yeah, if you're like overloading, you mean? I think that's a good question. That's a good question. I need to check, to be honest. I have never done it in Huff, so I don't know, but that's I don't even know if it works actually. Let me check, but that's a good question. Yeah, I don't know. I don't have the answer now, but all right, so we have like 10 minutes left, 12 exactly, but yeah, I think maybe you had enough. As you want. If you have more questions, feel free to ask them. I will be happy to answer them if you want to cut like a few more minutes, but otherwise, well, I just want to say thank you guys for, I lost the clicker again. Thank you guys for attending this workshop. I was pretty excited to see many people, and I was happy to see that you guys were staying until the end and working and building the contracts and even adding more stuff. So that's pretty cool. So yeah, that's it. You can, if you are interested, you can follow Huff on Twitter. There's the website. There's the Discord. We are working on Huff 2. The new compiler is being re-written from scratch. Actually, we are going to be working also on the EOF support and many other things. So yeah, feel free to follow for more good stuff.